Okay.
Hello everyone.
Hello everyone.
So today we
So
are
today we
starting
are
our
starting our
course of
course of
fundamentals of
fundamentals of
nano and quantum
nano and quantum
photonics. We are in the
photonics.
week
We are in the
11
week
of this
11 of
course,
this course.
and let me just share
We
the
just share
screen
the
first.
screen first.
Okay, yes.
Okay, yes.
Yours.
Yours.
So
So
just for
just for
recapping,
recapping,
so in the last
so in the
class
last class
we talked
we
about
talked
the
about
coherent
the
states,
coherent
the
states, the
quadratures,
quadratures,
and
and
0 point
zero
energy,
point
vacuum
energy, vacuum
fluctuations, vacuum
fluctuations, vacuum
energy, vacuum
energy,
field,
vacuum field,
and
and
we
at the
talked
end we
about
talked about the
squeezed
squeezed
light.
light.
Okay,
Okay,
so
so
we talked
we
about
talked
quantum
about
light,
quantum
and
light, and
then we
then we
introduced the
introduced
quadrature
the
and
quadrature
coherent
and coherent
states.
states.
So we saw
So we
that
saw that
quadratures x1
quadratures
and
x1
x2
and x2
that
that
correspond to
corresponds to
sine and
sine and
cosine
cosine
components of the field.
components of the
How?
field. How?
So we saw
So we
that
saw that
we saw that
we saw that
x1 equals
x1
to
equals to
epsilon naught v
epsilon naught v
upon 4h
upon
cross
4h
omega
cross omega
1 by 2
1 by 2
e naught
e naught
sine omega t.
sine omega t.
So
So
x1 is
x1
related
is
to
related to
sine
sine
component of the
component
field,
of the field,
which we wrote
which we wrote
omega by
omega by
2h cross
2h cross
1 by 2
1 by 2
q of
q of t.
Similarly,
Similarly,
x2 is equals
x2 is
to
equals to
epsilon naught v
epsilon naught v
4h cross
4h
omega
cross omega
1 by 2
1 by 2
e naught
e naught
cos omega t.
cos omega t.
So then
So then
x2 is
x2
related to
is
cos
related to
omega t,
cos omega t,
which we
which
write
we write
1 upon
1
2h
upon
cross
2h
omega
cross omega
1 by 2
1 by 2
pt.
pt.
So that is
So that is
quadratures x1
quadratures
and x2
x1 and x2
corresponds to the
corresponds to
sine and
the
cosine
sine and
component
cosine
of the field.
components of the field.
x1 is
x1 is
proportional to
proportional to
and
qt
x2 is
and x2
proportional
is
to pt.
proportional to
That is
pt. That
analogous
is
to
analogous to
position and moment.
position and momentum.
And
And
so
so
when we plotted
when we
it, we saw
plotted it, we
that
saw that
this is x1
this is
quadrature,
x1 quadrature,
this is
this
x2
is x2
quadrature,
quadrature,
and these are
and these
separated
are
by
separated by a
90-degree.
90-degree. Hence,
It's a
we can say it's a
quadrature.
quadrature.
So
So
And we saw
And
that
we saw that
these are the
these are the dimensionless
quantities.
quantities.
So we can
So
define
we
it
can define it dimensional
quadrature to
quadratures
normalize
to
the units.
normalize the units.
So x1
So
quadrature
x1
is
quadrature
defined in
is
terms
defined in
of
terms of
sine
sine
omega t
omega
and it
t,
is
and it
related
is
to
related to
generalized position,
generalized
that is
position,
qt.
that is qt.
x2 quadrature
x2
is defined
quadrature
as
is
cos
defined as
omega t
cos
and
omega
it
t,
is
and
related
it is
to
related to
generalized moment.
generalized momentum.
So
So
x1
x1
proportional to
proportional to
qt,
qt,
x2 proportional
x2
to pt.
proportional to pt.
So now
So
suppose
now
we have a
suppose we have
harmonic
a
oscillator
harmonic
here.
oscillator here.
So how it will
So how
evolve
it will evolve
in time?
in time?
So
So
we saw
we
that
saw that
when we have a
when we
pendulum,
have a pendulum,
just like
just like
pendulum
pendulum
oscillates back
oscillates
and forth.
back and forth,
Pendulum,
just
pendulum
like
oscillates
pendulum
back and
oscillates
forth
back and forth
from
from
extreme
extremes
position to
position
the
to the
center,
center, and
other
then
extrema,
other extrema,
another
then
center.
other center.
So at the
So
center
at
where
the
the
center where the
velocity will be
velocity will
maximum,
be
but the
maximum,
position
but the
will be
position
zero.
will be zero.
So
So
we can
we
suppose
can
that
suppose that
suppose we have
suppose we have
our harmonic
our harmonic oscillator
here.
here.
Okay.
Okay.
Now
Now,
if
if
it
it,
is at
it
zero,
is at zero,
now it
now
will
it
move
will
from
move from
this to
this
this.
to this.
So in
So
one
in
fourth of
one
the
fourth of
period,
the period,
suppose this is my
suppose this is
first
my
position,
first position,
this is my
this is my
position.
second position.
Okay.
Okay.
So
So
in
in
one fourth of the
one fourth
period,
of the
it
period,
will go
it
from
will
this
go
to this,
from this
one
to
to two.
this, 1 to 2.
In half the
In
period,
half
it
the
will
period, it
reach
will reach
from 2 to 3,
from 2 to 3,
and so
and
on.
so on.
Similarly, it
Similarly, it will
will like
like
this.
this.
Okay.
Okay.
So
So
effectively,
effectively,
we can
we
represent
can
our
represent
harmonic
our
oscillator
harmonic oscillator
by a
by
circle
a
in
circle in
x1 and an x2
x1 and an
plane.
x2 plane.
So
So
classical
classical
harmonic oscillator
harmonic
is
oscillator is
represented by the
represented by
circle.
the circle.
So we
So
can say
we
that
can say that
the plot
the
between
plot between
two
two
quantities in
quantities in
quadratures.
quadratures.
So the plot
So the
between
plot
two
between
quantities
two
in
quantities in
quadratures
quadratures
represent the motion
represent
of
the motion of
harmonic oscillator.
harmonic oscillator.
And
And
we saw that
we
in
saw
the
that
previous
in the
class
previous class
that
that
in quantum
in
picture it is
quantum picture
defined
it
as
is
the
defined
quantum
as the quantum
uncertainty.
uncertainty.
So we saw
So
that
we
delta
saw that delta
x1,
x1,
product of
the
delta
product
x1
of
is
delta x1 and
greater
delta
than
x2
1
is
by
greater
4,
than
there
1
is
by
no
4.
h
There
square
is no
because
h
these
square
are the
because these are the
dimensionless quantities.
dimensionless quantities.
So
So,
and with
and
minimum
with minimum
uncertainty state,
uncertainty state,
that is
that is
represent the
represent
coherent
the
state.
coherent state.
It is
It is
if it is
if it
vacuum
is vacuum
state, then it is
state, then
centered
it
at
is
0.
centered at 0.
And
And in phase space, in phase
circular
space circular
uncertainty.
uncertainty is.
So
So
what is the squeeze
what is
state
a
when the
squeeze state? When the
uncertainty becomes
uncertainty
an
becomes
ellipse?
an ellipse.
One
One
quadrature.
quadratures.
Okay.
Okay.
So this is
So
the
this is the
when
when
So this is the
So this is
quadrature.
the quadrature, and this is the reason of uncertainty.
This is a
This is a
phi. This
phi.
is
This
alpha.
is alpha,
Which represent the
which
amplitude.
represent the amplitude.
So
So
this is the
this is
quadrature
the
of. This
quadrature
is
of. This is
representing a
representing a
coherent state
coherent state
where the
where the
uncertainty is minimum.
uncertainty is minimum.
So we
So
cannot
we
talk of a
cannot talk
single
of a
sine wave,
single
but we
sine wave,
have
but we
to
have to,
coherent
for the
state. We
coherent
have to
state, we
talk
have to
about
talk about
the combination
the
of sine
combination of
waves.
sine waves.
So like how
So,
can
like,
we
how
represent
can we
it
represent
classically?
it
How can we
class?
think
How
about
can we
it
think about it
classically? So
classically? So,
classically,
classically, if we
derive the
drive the
twice of
pendulum
its
twice of its
natural
natural
frequency,
frequency,
the position
the
gets
position gets
exponentially amplified
exponentially amplified
and the momentum
and the
gets
momentum gets
attenuated.
attenuated.
So
So,
effectively
effectively
squeezed and the
squeezed and the
position.
position.
So
So,
effectively in the one
effectively, in the
direction it
one
is
direction, it
squeezed
is
and the
squeezed
position
and the
becomes
position becomes
exponentially
exponentially
larger.
larger.
So
So,
the coherent
the
state
coherent state
converted into
converted into, suppose,
x1,
x1,
x2.
x2.
If it is like
If
this
it is like
class,
this classic, just
so it
so
is
it
squeezed.
is squeezed.
This is
This is
x1
so
was
x1 was
proportional to q,
proportional to
x2 was
q, x2
proportional
was
to p.
proportional to p.
So now you
So
can see
now you can
that
see that
the uncertainty
the
is in
uncertainty
x2.
is in x2.
This is
This is
momentum
momentum
squeeze oscillator.
squeeze oscillation.
That is
That is,
one quadrature's
one quadrature's
uncertainty
uncertainty
decreases
decreases
while the
while the
other
other
quadratures
quadratures
while the other
while the
quadrature
other quadrature
increases.
it
But the
increases.
product
But the
remains
product
constant
remains
and it will still
constant and it
satisfy the
will still satisfy the
uncertainty principle.
uncertainty
So how
principle.
can we
So
understand
how can we
squeezing?
understand
So
squeezing?
squeezing
So squeezing
is
will
reducing
is
noises to
reducing
one
noises
quadrature
one quadrature
below short
below
noise.
short noise.
So we have
So we have
understood the classical
understood the
analogy that
classical
is the
analogy,
driven
that is the
harmonic
driven
oscillator.
harmonic oscillator.
Modulation less to the
Modulation leads
unequal
to the
amplitude
unequal
and
amplitude and momentum
fluctuations.
fluctuations.
So on phase
So
float,
on phase float,
orbit will
circular
become
orbit will
elliptical
become
and that
elliptical, and
can
that
represent
can
either
represent
momentum
either
or amplitude
momentum or
squeeze.
amplitude squeezing.
So
So
what is so
what is
here is a
here
table
is a table
where we
where
showed
we
the
showed
coherent
the
versus
coherent
squeeze line.
versus squeeze light.
So
So
for the
in for the
coherent, so if the
coherent, so
property
if
is
the
delta
property is
x1
delta
is equal to
x1 is
delta
equals to
x2 is
delta
equal to
x2 is
half
equals
of. So
to half of, representing
it
it
is
is
representing
representing the circle.
when the
When the
uncertainty
uncertainty
delta
in
x1
delta
delta x2
x1
equals
delta
to
x2
half.
equals to
So
half.
it is a
So it
coherent
is a
state,
coherent
not
state,
squeezed.
not squeeze state.
So when we
So when we
phase
see the
space
phase space
shape, if it is a
shape, if
circle,
it is
then
a
it's
circle, then
coherent
it's
state.
coherent state.
If it is an
If it is
ellipse
an
like
ellipse like this or
this,
like
then
this,
it's a
then
squeeze
it's
state.
a squeeze state.
So the shape
So
of the
the
phase
shape of the
space
phase space
is circle for
is circle
coherent
for coherent
and
and
squeezed for
squeeze for
elliptical.
elliptical.
For the coherent
For the
state,
coherent state,
noise is equal
noise
in
is
all
equal in
direction
all direction
because it's circle,
because it's circle,
but it is
but it
reduced
is
in
reduced in
one direction
one
or
direction
increased
or
in the other.
increased in the other.
So now,
So now,
what is the photon
what is the photon
statistics? So we saw
statistics?
that
So we
for
saw
the
that for
coherent
the
state,
coherent states,
photon
photon
statistics is
statistics is
Poissonian,
Poissonian,
while for the
while
squeeze
for
state,
the
it
squeeze
can be
state, it can be
sub-Poissonian or
sub-Poissonian or
super-Poissonian.
super-Poissonian.
So there are two
So
types
there are two
we can
types. We
define
can define
the types of
the
squeeze
types
light.
of squeeze
There
lights.
are two types
There
of
are two
squeeze
types
light.
of squeeze lights.
One is the
One is
amplitude
the
squeeze light
amplitude
and
squeeze
the other
light,
one is
and the other
phase.
one is phase squeeze light.
So
So
in amplitude
in
squeeze light,
amplitude squeeze light,
delta x1
delta x1
is lesser than
is
1
lesser than 1 by 2
and delta
and
x2
delta
is greater
x2
than
is
1.
greater than 1 by 2.
Whereas,
Whereas
okay, so we'll see. So let's
plus
putting up
I'm
a
putting up
question.
a question.
This
If
is
this is
x1,
x1,
and this is
this is
x2, and
x2,
you have a.
and you have a circle.
So this is a
So this is a
coherent state or
coherent
vacuum
state or
state.
vacuum state.
So it's
So
a
it's a
vacuum state.
vacuum state.
Why vacuum
Why
state?
vacuum state?
Since
Since
there is no
there
photon.
is no photon.
Since the circle
Since
is
the
at
circle is
center,
at center,
the circle is
the
at
circle is
center,
at center,
and
and
delta x1 is
delta
equal to
x1 is
delta
equal
x
to
is equal
delta
to
x
1
is
by
equal to
2.
1 by
So the
2.
product
So
is
the
with minimum
product is with minimum
uncertainty. We
uncertainty.
can call
We
it a
can call it a
coherent vacuum
coherent
state
vacuum state.
because there
Because
is no
there is
amplitude,
no
there is no
amplitude,
alpha.
there is no alpha.
Delta n bar,
Delta n by
delta n is
delta
0.
n is
So
0.
delta n
So
is 0
delta n
means
is 0 means
it's a vacuum
it's a
state.
vacuum state.
And
And
so if we
so
had to
if we had
represent
to
another
represent
state which has
another state which
500
has 500
photons,
photons,
so then it will
so
be,
then it will be,
so that
we
we can
saw that we can directly represent it
this
as this
root 500.
root 500.
Okay,
Okay.
all right. Now
Now when we
when we will try
when we
to
will try
squeeze
to
it,
squeeze it,
so we saw
so
that
we
Q
saw
and P
that
are
Q and
related
P are
to
related to the
electric field.
electric
So
field. So
it's a
it's a
coherent vacuum
coherent
state,
vacuum
whereas
state,
it
whereas
is
it is
normal coherent
normal
state.
coherent state.
So now when we
So
will
now
try
when we
to
will
squeeze
try
it,
to
that is
squeeze
Q
it,
and
that
P
is
are
Q
related
and
to
P are
electric
related to
field.
electric field.
So
So
the way
the
fields
way
are,
fields
electric
are,
fields are
electric
getting
fields are
changed.
getting changed.
So the
So
electric
the
field
electric field
will change
will
when the
change
shape
when
will
the
change.
shape will change.
So then
So then
we can
we
draw
can draw
the
the
squeezing in
squeezing in
amplitude as well
amplitude
as
as well
phase.
as phase.
So this is
So this is
normal coherent
normal
state.
coherent state.
Squeeze it.
Squeeze it.
So now
So now
it will be
it
delta
will be
phi.
delta phi.
This is
This
x1.
is x1.
This is x2.
This is x2.
So now
So now
this
this
stretched region.
stretched region,
This stretched
this
region.
stretched region,
The stretching
the
region of
stretching region of
uncertainty is
uncertainties
radially,
radially,
and we
and
have
we have
compressed the
compressed the
azimuthal angle.
azimuthal angle.
So
So
increasing the
increasing the
uncertainty in
uncertainty in
number of
number
photons.
of photons.
So in this
So in
case,
this case,
in this
in
case,
this case,
since it is
since it is the
the uncertainty is
uncertainty is increased
radially,
radially,
so number of
so number of
bar,
photons n bar
delta n bar
delta n bar
increases
increases
and delta phi
and delta phi
decreases.
decreases.
So this is if
So this
delta
is
phi
if
is
delta phi
decreasing,
is
then
decreasing, then
what does this
what
mean?
does this
This
mean?
is
This is
phase
phase
squeezed
squeezed
it.
by it.
Next is
Next is
if
if
if the squeezing
if the
is like
squeezing is like
this,
this,
So now
So now
here
here
the stretching
the
is
stretching is along
azimuthal
azimuthal
angular direction
angular direction
and
and
compression
compression
along
along
radial direction.
radial direction.
Okay,
Okay.
so
So
this is
this is
so photo
so
if there
photo
is
if
decrease
there is decrement
compression in
compression in
radial direction,
radial
then we know
direction,
that
then we know that
the photon
the
number
photon number
corresponds to the
corresponds to the
photon number
photon number
corresponds to the
corresponds to the
amplitude of
amplitude of
electric field.
electric
Okay,
field. Okay.
so
So
it means there
it
is
means
decrease
there
in
is decrease in
amplitude of
amplitude
electric
of
field, so
electric
that's
field.
why
So that's why it is
amplitude square.
amplitude squeeze light.
Okay, so now
Okay.
what
So
about
now what about the photon
statistics for the
statistics?
phase
For the
square
phase
light?
squeeze light,
For the phase
for the
square light,
phase squeeze
we
light,
saw that
we saw that
delta x1 is
delta
greater
x1
than
is
1
greater
by
than
2,
1
delta
by
x2
2,
is
delta
lesser
x2
than
is
1,
lesser than 1 by 2,
and
and
delta n
delta
is
n is
greater than
greater than
root n
root
bar,
n bar,
because
because
number of
the number of
photons
photons
increased. If it
increase.
is increased, it means
It
delta
means delta n is
n
greater
bar
than n bar and
will
it
follow the
will follow the
superposition.
superposition.
Whereas in case
Whereas in
of
case of
amplitude squeeze
amplitude
light,
squeeze light,
amplitude squeeze
amplitude
light,
squeeze light,
delta n is
delta n is
lesser than n
lesser
bar,
than n bar,
and then it will
and then
follow
it
the
will follow the
subposition.
subposition.
So till now
Till now,
we saw
we saw
the
the
fluctuations, we saw
fluctuations,
the
we
photon
saw the photon
statistics
statistics
based on the
based on the
fluctuations in number of
fluctuations in
photons.
number of photons.
Similarly, we can have
Similarly, we
phase
can have
statistics
phase
also.
statistics also.
So
So
we can draw.
we can draw.
So
So
remember in the
remember,
last
in the last
lectures we
lectures we
drew some
drew some
histograms to
histograms
define
to define
the photon
the photon
statistics
statistics
based on the
based on the
fluctuations in number of
fluctuations in number of
photons. So
photons.
just
So
like
just
here
like
also,
here
we
also,
can draw
we
the
can draw the
histogram for phi.
histogram for phi.
So we can draw
So
the
we can draw the
histogram for
histogram
phi.
of phi.
This is phi.
This is phi.
This is
This is
probability.
probability.
This is no.
This is no.
So here
So here
the width of
the width of
histogram,
histogram,
the width of
the width of
histogram will
histogram
represent
will
the
represent the
uncertainty in the
uncertainty in the
phase. Just
phase.
like width
Just
of
like width
Poissonian
of
distribution
Poissonian
of delta.
distribution was delta n.
So for
So
the phase
for the
squeeze
phase
light,
squeeze light,
delta phi will
delta
be
phi will
smaller
be smaller
and
and
amplitude becomes
amplitude
super
becomes
Poissonian.
super Poissonian.
So suppose
So suppose
if I'm
if
plotting
I'm plotting
P of phi
P of phi
and phi.
and phi.
So one
So one,
for a
so
general
for a general
state,
coherent state,
so here we have
so here we
these
have
three
these
cases.
three cases.
So
So
if there is
if there is
reduction
reduction in
If there is
If there is
increment in n,
increment in n,
it means there
it
is
means there is
decrement in
decrement
phase.
in phase.
So
So
red color
red color represents
the red plot
red
represents
plot
phase
represents
squeeze.
phase squeeze.
Whereas if there
Whereas
is
if there is
decrement in the
decrement in the
number of
number of number of
photons,
photons,
then
then
so for phase
so
squeeze
for
light
phase
delta
squeeze
phi
light
will
delta
be
phi will
smaller
be smaller
and amplitude
and
becomes
amplitude becomes
super Poisson.
super
That's
Poissonian.
why we
So
saw
that's
that
why we saw that
delta phi will be
delta
greater than
phi will be greater than 1 by 2
and the
and
statistics
the
will become
statistics
super
will
Poisson.
become super Poissonian.
And
And
for this
for
case,
this case,
this is
this is
amplitude squeeze
amplitude
light
squeeze
where
light where
the number of
the
photons
number
will
of photons
reduce,
is
but
reduced,
the
but the
uncertainty in phase
uncertainty
has
in phase
increased.
has increased.
So it is
So it is
so what is the
so
physical
what is the physical
interpretation for this?
interpretation for
So
this?
phase
So
squeeze
phase
means
squeeze means
so phase
so
squeeze
phase
means
squeeze means
there are
there are certain
time
instant time
instants
instants
where the
where the
uncertainty in the phase
uncertainty
is
in the phase
actually
is
smaller
actually
than the
smaller
coherent
than the
state.
coherent state.
So,
So right,
if we have the
if we
squeeze
have the
light in
squeeze
along
light
this
in along
direction,
this direction,
and if we
and
will
if
take
we will
the
take the
projection on
projection
x1,
on
then
x1,
this will
then
start
this
with
will
this,
start with this,
and
and
here it will like
here it will like
this,
this,
become
here it will
again,
become again,
and here it
and here it will become again.
okay.
Okay.
So if we will
So
take
if
the
we will take
projection
the
on that, you
projection
can
on
see
that,
that
you can
here
see
it will
that
be
here it
this.
will be this.
After
After
it will become
it will
larger.
become larger.
So this
So this
the
the
uncertainty has
uncertainty has
increased.
increased.
But again at
But
this
again at
point
this point
it has again
it has
reduced,
again
then
reduced,
again
then again
increased,
increase,
then again.
then again reduced.
So it means
So it
there
means
are certain
there are certain
time
time
instants where the
instants where the
uncertainty in the phase is
uncertainty in the
actually
phase is
smaller than
actually
this. So
smaller
at
than the.
these
So at
points,
these points,
delta phi
delta phi
is lesser
is
than
lesser
delta
than
phi
delta phi
coherent.
coherent.
But
But
it doesn't mean that
it doesn't
all
mean
the
that
time
all the time
instance phase is
instance
less.
phase is less.
So
So
whereas for
whereas
the
for
amplitude
the
squeeze
amplitude
states,
squeeze states,
for the
for
amplitude
the
squeeze, this
amplitude
was the
this
phase
was the
squeeze state.
phase squeeze states.
For the
For
amplitude
the
squeezed,
amplitude squeezed,
so for
so
first
for
it is like
first it is like
this,
this,
then
then
this,
this,
this.
this.
If we will
If we will
take the
take
projection
the
of this one
projection on x1
on the graph,
on the graph,
will
it will
okay.
okay.
And
And
in this case,
in this
at
case,
these
at these
points,
points,
amplitude
amplitude
fluctuations
fluctuations
is smaller
is
than
smaller than
delta A
delta
coherent.
A coherent.
Not at all
Not
the
at
time
all the time
instances, just for
instances, just
certain
for
time
certain time
instances.
instances.
We will see
We
that
will see
like
that like
uncertainty in phase
uncertainty in
or
phase or
uncertainty,
uncertainty is
like for
like
the case of
for
phase
the case
state,
of phase state,
uncertainty in phase is
uncertainty
lesser
in
than
phase is lesser
coherent
than
state.
coherent state.
Similarly, for the
Similarly, for the
amplitude state,
amplitude state,
uncertainty in
uncertainty in
amplitude is smaller than
amplitude is
the
smaller than the
incoherent.
A coherent.
So in
So
coherent
in
state,
coherent state, what
we saw that
will
in
we say that
coherent
in
state the
coherent state the
fluctuations are
fluctuations
constant
are
in time. But
constant
in
in
case of
time. But
phase
in
or
case of
amplitude
phase or
squeeze state,
amplitude squeeze
fluctuation
state,
changes as
fluctuation
a function.
changes as a function of time.
So it's
So
changing with
it's
time as
changing
a
with
function
time
of
as a
time.
function of time.
So
So
we saw that
we
delta
saw that
x1,
delta x1,
delta x2
delta x2
is greater than
is
1 by
greater
4.
than 1 by
Similarly,
4. Similarly,
delta phi is greater
delta
than 1
phi is
by
greater
2,
than 1 by 2,
where n is
where
represented the
n is
photon
represent the
number, delta
photon
phi
number,
is the
delta
phase.
phi is the phase.
So
So,
what happens if
what
delta
happens if
n is
delta n is
small? So
small?
delta
So,
n
if
is
delta
small,
n is small,
delta phi
delta phi,
delta phi
delta
is equals
phi
to
is equals to
1 by 2
1 by
delta n.
2 delta n.
So as
So,
delta
as
n
delta
decreases,
n decreases,
delta
delta
delta n
delta
decreases,
n
delta
decreases,
phi will
delta phi
increase.
will increase.
So
So,
what will happen
what
if
will
delta phi
happen if
will be
delta
greater
phi
than
will
2
be
pi?
greater than 2 pi?
So now the
So
phase will
now the
become
phase will
undefined.
become undefined.
So
So
uncertainty in phase
uncertainty in
itself is
phase
2
itself
pi,
is 2 pi,
and the phase
and phase
can go from
can go
0 to
from
2 pi.
0 to
If we
2 pi.
cross 2
If we
pi,
cross 2 pi,
it will
it will
circles back,
circles back,
right? Like after 2
right?
pi, we
Like
can
after 2
wrap
pi, we can
it up
wrap
into
it
the
up
angles of
into
2
the
pi.
angles of 2 pi.
So if
So
delta phi
if
is
delta
greater than
phi is
2
greater
pi,
than 2 pi,
uncertainty
uncertainty
will be very
will be
large.
very large.
If
If
uncertainty will be large,
uncertainty will be large,
if
if
uncertainty will be large,
uncertainty will be large,
it means
it
phase
means
is undefined.
phase is undefined.
So for
So
example,
for
photon
example,
number
photon
states.
number states.
So in case
So
of
in case of
photon number
photon
states,
number states,
delta n is
delta
equals
n
to
is
0.
equals to
That
0.
is
That
fluctuations
is
in
fluctuations
photons
in
are 0.
photons are 0.
So here
So
in the
here
slide
in
we
the
saw that
slide we saw that
if amplitude
if
squeeze
amplitude
smaller
squeeze
delta n
smaller
larger
delta and
phi,
larger phi,
phase squeeze
phase
larger
squeeze
del n
larger del
smaller
and
del phi.
smaller del phi.
And in with
And in
time,
with time,
for the coherent
for the
state, there is
coherent state, there
constant
is
field noise
constant
over
field
time.
noise over time,
Whereas for the
whereas
squeeze
for the
state,
squeeze
noise
state,
varies
noise varies
periodically as
periodically
ellipse
as
rotates.
ellipse rotates.
So
So
electric field
electric field
it means
it means
electric field
electric field
uncertainty is
uncertainty
oscillating
is
lower at
oscillating
certain
lower at
time
certain
than
time
the coherent
than
time.
the coherent time.
So now
So now
photon number
photon
states.
number
So we
states. So we
defining is at
defining is at
n ket. So
n ket.
exactly
So
n photon.
exactly
So
n photons.
suppose
So suppose
if delta
if
n
delta
is equals
n
to
is
0,
equals
that
to
is
0, that is
fluctuations in photons
fluctuations
are
in
0.
photons are 0.
It's a
It's
perfect
a perfect
subpoisonion
subpoisonion line.
light.
Light.
Also,
Also,
photons are
photons
equally
are
spaced.
equally spaced.
So if we
So if
make a
we make
measurement
a
for 1
measurement
second
for 1 second
and find one
and find
photon,
one photon,
so the
so
finding
the
one
finding
photon
one
it
photon,
represents the
it
photon
represents the
number state
photon
is
number
equals to
state is
1.
equals to 1.
And if 5
And if
photon,
5
then number
photons,
of
the
states
number
is
of
5.
states is 5.
So
So
for the delta
for the
n is
delta
equals to
n is
0,
equals to 0,
that circle
that circle
represents
represents
photon number
photon
states,
number states,
where the radius
where the radius of
circle
circle
represents
represents
number of
number of
photons.
photons.
Okay,
Okay,
so
so
in this case,
in this case,
when
when
delta n is
delta
equals to
n is
0,
equals to
it
0,
means the
it
phase
means the
is
phase is
undefined.
undefined.
For the
For
suppose
the
for the perfect
for the perfect
subpolynomial case,
subpoisonion
okay,
case. Okay,
in phase
in phase
fixed
phase
energy
fixed
random
energy
phase.
random
Okay,
phase. Okay,
so
so
is this
is this
possible?
possible?
Is the
If
reverse
the
case
reverse
is also
case is
possible
also
where phase
possible
is
where
defined
phase is defined
completely and
completely
we have the
and we
complete
have the completely unknown photon number.
so there is no such
There is
case.
no such
In that
in that
in case of
in case of
undefined phase, we can
undefined
think
phase,
of
we can
okay the
think of
number of
okay, the
photons
number of
is
photons is
zero.
0.
The delta n is
The
equals
delta n
to
is
zero
equals
and we
to
can
0
have the
and we can have the
subpolynomial case.
subpoisonion case.
But the reverse
But
case
the
cannot
reverse case
happen.
cannot happen.
And
And
we saw that
we
with
saw that with
no photons,
no
field shows
photons, field shows
fluctuations,
fluctuations,
average electric
average
field is
electric
zero,
field is 0,
variance is
but
not equal
variance
to
is
zero,
not
and it
equal
is
to 0 and it
responsible
is
for
responsible for the
spontaneous emission,
spontaneous emission, 0 point
energy Casimir
energy
effect.
Casimir effect.
One
One
important not
important
thing to note
thing
here is
what there is
photon number
photon
states are
number
not
states are
minimum
not minimum
uncertainty states.
uncertainty states.
As n
As
increases,
n increases,
uncertainty product
uncertainty
also
product also
increases.
increases.
Then
Then
where do we
where do we
where can we
where
find the
can we
utility
find
of
the
all
utility
these
of all
things?
these
We are
things? We are
considering the squeeze
considering the
state and
squeeze state
all these things.
and all these
So
things.
this is the
So this is the
gravitational wave
gravitational waves
and LIGO
and LIGO
and the LIGO
and the
experiment.
LIGO experiment.
So
So
Einstein
Einstein in
1916 predicted
1916
regarding the
predicted regarding
gravitational
the
waves.
gravitational waves.
He stated
He
that
stated that
an object,
an object,
if we have an
we
object
have
of
an
spherical
object of
shape,
spherical
and when
shape,
the
and
gravity
when the
wave
gravity
passes
waves
through that,
passes through that,
there is a
there is a
slight
slight
elongation in one
elongation in
axis
one
and
axis
compression
and
along the
compression
other.
along the other.
That is, an
That is,
object will
an
slightly
object will
stretches
slightly stretches
or compresses
or compresses
in one or
in
the other
one or the
direction
other
as the
direction as
gravitational
the
wave passes
gravitational
through.
wave passes through.
So
So
basically,
basically,
the sphere
the
will become
sphere will become
ellipse.
ellipse.
Okay.
Okay.
So with time,
So with
the
time,
axis of
the axis of
compression and
compression and
elongation is
elongation is
changing,
changing,
and
and the
gravity
this
waves
gravity
occur
waves occur
when some
when some
cosmological event
cosmological event
like
like
supernova or
supernova or
cosmological energy which
cosmological
have
energy
very
which
high
have very
energy
high energy
that can cause
that
the
can
gravity
cause the
waves to
gravity
go through
waves to
the
go through the
space. So
space.
suppose
So
if we
suppose
have
if we have
so
so
this is a
this
gravity
is a
wave
gravity wave
at
at
zero time,
zero
it's
time,
like
it's
this,
like this,
0.5
zero point
seconds,
0.5 seconds,
like
like
this,
this,
one,
one,
it again
it
become like
again
this.
become like this.
So this is a
So this is a
change
change
in the
in the
length.
length.
So that delta
That
L
delta L
by L is
by L
the
is
order of
the
10
order of
raised to power
10 raised to
minus
power minus
1
21
nanometer, that is less
nanometer.
than
That
the
is less than the
atometer.
atometer.
Atometer is of the
Atometer
order
is
of
of the order of
10 raised to power
10 raised to
minus
power
18.
minus 18.
It is even
It is
lesser than
even
that.
lesser than that.
So,
So,
so L is the
L is
diameter
the diameter
and delta L
and
is
delta L
stretching
is
or
stretching or
compression length.
compression length.
So change in
So
the
change
path.
in the path.
So how
So
it's
how
got
it's
observed.
got observed.
So how can
So
we
how
measure?
can we make
So we had
So
a
we
laser,
had a laser,
and then there is
and
a
then
beam
there is a
splitter.
beam splitter.
BS is a
BS is representing the beam.
so,
So,
so
so
then it
then
passed
it
through a
passed
beam
through a
splitter.
beam splitter.
What is happening
What is
here?
happening
So
here?
here
So here
we have one
we
laser.
have one laser,
This is beam
and this is
splitter.
beam splitter.
The
The
after beam splitter,
after
it is
beam splitter,
divided
it is
into two
divided into
parts,
two parts,
and here we
and
have
here we have
one mirror, and
one
here
mirror, and
the
here
other mirror,
the
and
other
these are
mirror, and these
suspended.
are
So
suspended.
we can
So
change
we
the
can change the
delta L.
delta L.
So
So
change
the
is
change
an
is an
interference.
interferometer.
After
So after
reflecting through these
reflecting
two
through these
mirrors,
two
it
mirrors,
will come
it will
again
come
at the
again at the
beam splitter,
beam splitter,
and then
and then
at the beam
at the
splitter,
beam splitter,
it will
it will
interfere and will
interfere
give,
and
provide
will
us
give,
the
provide us the
output.
output.
So
So
the change in
the
path
change in
length,
path length,
since the mirrors are
since the
the
mirrors are
change in
the
path
change in
length
path
will
length
produce
will
a
produce a
shifted
shift in
interference pattern.
interference pattern.
Okay,
Okay,
and then by
and
measuring
then by
how many
measuring how
fringes are
many fringes
shifting,
are
we can
shifting, we
calculate
can
the how much
calculate
is
the
the
how
change
much is
in
the
the path.
change in the path.
So
So
here we have
here we
two
have the two
suspended mirrors
suspended mirror
perpendicular to each
perpendicular to
other,
each other,
and
and if
if the
if
stretching
the
is n,
stretching is n,
if stretching in
if
the one
stretching in the
direction,
one
then
direction, then
compression in the other.
compression in the other.
So we
So
can solve
we
one
can solve
example
one
for that.
example for that.
Like how can we
Like how
change
can we change in
delta L?
delta L?
So let's
So
assume
let's
that
assume
lambda
that
is
lambda is
lambda is 1064
1064
nanometer
nanometer
and power is
and power is
300 watt.
300 volt.
So we want to
So we want to
calculate
calculate
delta L.
delta L.
So
So
lambda
lambda
in electron
in
volt we can
electron volt we
calculate
can calculate
1.24,
1.24,
which will
which will
give us the
give us the
1.17 electron.
1.17 electron
Now we
volt.
can
Now we can
calculate the phi,
calculate the phi,
which is
which is
flux, which we
flux, which
calculated.
we calculated.
This we have
This
done
we have
this in
done
previous
this in
class
previous
also.
class also.
Electron volt,
Electron volt
300 watt
300 watt
upon
upon
1.17
1.17 into 1.6
into 10 to the
into
power
10
minus
to the power
19,
minus 19,
which will give us
which
the
will give us the
1.6 into 10 to
1.6 into
the power
10 raised to
21
power 21
photons per
photons
second.
per second.
Okay.
Okay.
So now
So now
n bar is
n bar is
delta n.
delta n,
1.6 into 10 to
1.6
the
into
power
10 raised to power
21
21
photons.
photons.
And delta
And delta n
is equals to
is
n
equals
bar,
to n
so
bar,
4
which is
into 10
4
to the
into
power
10 raised
10.
to power 10.
Now using
Now using the uncertainty relation
between number
between number
and phase
and
delta
phase,
and delta
delta
phi
and
is
delta
greater
phi
than.
is greater than.
is equals to
is
1 by
equals to 1 by 2.
delta pi is
Delta
equals to
pi
1
is
by
equals
2,
to 1 by 2 delta n,
which will give
which will
us
give
the
us the
1.25
1.25 into 10 raised to
11.
power 11 radians.
Now,
Now,
delta L by
delta
lambda
L by lambda
greater
is
than
greater
delta
than
pi by
delta
2
phi by 2 pi.
1.25
1.25
into
into
1.06
1.06
because
because
1064.
1064 nanometer.
This will
This will
give us
give
approx
us
10 raised
approx
to
10
power
raised to
8.
power 18.
So with this
So with this
interferometer,
interferometer,
the minimum
the minimum
change in
age
the
in
length
the
that we can
length
detect
that we
is
can
10 raised
detect
to
is
power
10 raised to
minus
power
18.
minus 18.
Then how
Then
did we
how
achieve the
did we
10 raised
achieve
to
the
power
10 raised to
minus
power
20?
minus 21 limit?
So to
So to
achieve 10 raised to
achieve
power
10 raised to power
minus 21
minus
limit,
21 limit,
we have to
we
have
have to
range of
have range
L
of
in
L in
kilometers
kilometers
so that we can
so that
reach
we
up to
can
10 raised
reach
to
up to
power
10 raised
minus
to power
21
minus
limit.
21 limit.
Because
Because
here
here
with this
with this
thing, we can
thing, we can
calculate our
calculate
short noise
our short
limit
noise
to
is
10 raised to
limited to
power
10 raised to
minus
power minus
18. So delta
18. So
L we can
delta
detect
L
is
we can
10 raised
detect
to
is
power
10 raised
minus
to power
18.
minus 18.
So now
So now we
if we
have,
want to
if we want
increase
to
it,
increase
if we want
it, if
to
we want to
improve the
improve
detection,
the
we
detection,
have to
then we
take
have to
L
take
very
Ln
large.
very large.
So
So
what
what
were the legal
were the legal
achievements?
achievements?
Like they
Like they
proposed
proposed in
1960s and
1960s, and
then they got
then they
funds.
got funds.
There was very
There was
massive
very massive
collaboration
collaboration
investment
and
with this,
investment with this,
and
and
gravitational waves
gravitational
were
waves
detected
were
first time in
detected first time in
2015 and got the
2015
Nobel
and got the
Prize in
Nobel Prize in
2017.
2017.
And
And
now how can we
now how
increase
can we
the
increase the
sensitivity beyond
sensitivity
short
beyond
noise?
short noise?
So short
So
noise we
short
can't.
noise we can't,
Short noise set a
short noise set
fundamental
a
limit in
fundamental limit in
interferometry.
interferometry.
So
So
can we go
can we
below it?
go below
Yes,
it?
we saw
Yes, we saw
sub
in case of
Poissonian or squeeze
sub-Poissonian or
light.
squeeze
We
light,
can
we
reduce
can
the
reduce the
quantum fluctuation
quantum
in one
fluctuation in
quadrature.
one
That is,
quadrature. That is,
in one
in
direction it is
one
going
direction it
below
is
short
going
noise.
below short
So
noise.
it can we
So
can increase
we can
the
increase the
sensitivity.
sensitivity.
And LIGO
And
actually
LIGO
uses
actually
squeeze
uses
light
squeeze light
to improve
to
the
improve the
further sensitivity.
further sensitivity.
Now,
Now,
how can we
how
detect
can we detect
the squeeze
the
states?
squeeze states?
So for the
So for
detection
the
of squeeze
detection of
state,
squeeze
we use the
state, we use
homodyne
the
detection
homodyne
scheme.
detection scheme.
So we saw
So
that
we saw
one of the
that one
detection
of the
scheme was
detection scheme was
balanced photo
balanced
detection,
photo detection,
where we were
where we
combining
were
a small.
combining a small.
So in
So
general,
in
small
general,
signal
small
is
signal is
difficult to measure.
difficult to measure.
So to detect
So to
that,
detect that,
what we can do?
what we can do?
We can take a
We can
strong
take a
signal
strong
and a weak
signal and
signal.
a weak signal.
So we can
So you
think it
can
like
think it
this.
like this.
So we have
So we have
I1
I1,
photodetector
photo detector 1, photo
2,
detector
I
2,
2,
I2,
beam splitter,
beam splitter,
electric fence.
electric piston.
Okay, so
Okay,
this is the
so this is
schematic.
the schematic.
Yes.
Yes.
Okay.
Okay.
So now
So now
here we are taking
here
a
we are
strong
taking a
signal
strong
ES
signal
and a weak
ES and a weak
strong
a
signal
strong
LO.
signal LO.
Strong input is
Strong
called the
input is
local
called the
oscillator.
local
This is
oscillator.
LO.
This is LO.
And
And
when
when
we are
we are
combining a weak
combining a
quantum
weak
signal that
quantum
is
signal
ES
that
with a
is
strong
ES with a
local
strong
oscillator,
local oscillator,
and then we are
and
using
then we are
50
using a
beam
50-50
filter
beam
and
filter
balanced
and balanced
photodetectors. So
photodetectors.
what we will
So
do
what we will do
after
after
photodetector 1 there is
photodetector 1 there
I1
is I1
and
and
photodetector 2 is
photodetector 2
I2,
is I2,
and in the
and in
output
the
when these
output
two are
when these two are
interfering,
interfering,
these two signals
these two
will
signal
interfere,
will
and after
interfere, and
passing through
after passing through
photodetectors
photodetectors
they will
they will
combine and then
combine and
integrate,
then
and we will
integrate,
measure
and
the
we will
difference
measure the
in their
difference in their
currents.
currents.
So
So
the short noise
the short
will
noise
reflect
will
in the
reflect in
photocurrent.
the photocurrent.
So
So
without signal
without signal,
there will be
there
output
will be output
fluctuation that will give
fluctuations
you the
that will
short
give you the
noise.
short noise.
With squeeze
With
signals,
squeeze signals,
fluctuations will
fluctuations
fall
will
down below
fall
the
down
short
below
noise
the short noise,
and it will show the
and it will
quantum
show the
signature.
quantum
And
signatures.
we can
And we
use it
can
for
use it for the
phase sensitive
phase
detection of
sensitive
squeeze
detection of
light.
squeeze light.
So
So
for the case of
for the case of
subpoisoning,
subpoisoning,
delta n is
delta
lesser
n
than
is
n
lesser
bar.
than n bar.
Amplitude squeeze
Amplitude
that is
squeeze
delta
that is
I,
delta I,
that is the
that
it's
is the
below
it's
short
below
noise.
short
That's
noise.
mean
That's mean
intensity fluctuations
intensity
are reduced,
fluctuations are reduced,
and for the phase
and for
speed
the
that is
phase
opposite
speed that is
behavior, that
opposite
is
behavior, that is
fluctuations in
fluctuations in
phase are
phase are
minimized.
minimized.
So
So
the
the
schematically we can
schematically we can
represent it
represent
as
it as
this is a
this is a
capacitor.
capacitor.
Here is minus
Here is minus
node,
V naught, V naught. This is
this is
photodetector
for
1. This is
detector 2.
photodetector 2.
Here is
Here
going,
is going.
here is
Here is
load resistance,
load resistance.
here is
Here is
capacitor,
capacitor.
AC
AC
component,
component.
and here we are
And here we are measuring
measuring
the output.
one signal is
One signal
here,
is going here. One signal is going here.
and
And
here it's going
here it's going
I1,
I1,
I2.
I2.
Here there will be
Here there will be difference
difference.
I1 minus
So the
I2.
two
So the
balanced
two balanced
photodetectors are
photodetectors
biased
are biased
uh,
uh,
in a way that
in
the
a way
overall
that the
fluctuation
overall
in the current
fluctuation
will
in the
vanish
current will vanish
between the
between the
detectors, and
detectors,
only the
and
AC
only the
component
AC
is there,
component is left,
which is short noise
which is short
fluctuation.
noise
We can
fluctuation,
measure
and we
the
can measure
output
as the output
VT.
Vt.
So
So
fluctuation in the current
fluctuations in the current
effectively captures the
effectively captures the
fluctuations in the
fluctuations in the
intensity.
intensity.
So now,
So now,
how can we
how can
generate
we generate
the squeeze
the
state?
squeeze
So
state?
it arises
So it
from
arises
the
from the
nonlinear optical
nonlinear
effects.
optical effects.
So
So
suppose we have
suppose we
a
have a
crystal
nonlinear crystal,
and we are
and we are giving,
and it
and
has
it has
non-system, it
nonlinear
has
crystal,
light.
it has chi to non-zero.
So we are
So we are
suppose signal
suppose signal
omega 1
omega 1
and pump
and pump
frequencies to
frequencies to
omega 2
omega 2
LR. Okay.
LF. Okay.
So omega
So
2
omega 2
will be 2
can
omega.
be 2 omega minus omega
So
1.
this is the
So this is
parametric
the parametric down
conversion. So
conversion. So
polarization
polarization
expansion is
expansion is
this. PT
this.
is equals to
PT is
epsilon
equals to
naught
epsilon naught
chi 1 ET
chi
plus
1 ET
epsilon chi
plus
2
epsilon
ET.
chi 2 ET.
These
So these
represent the
represent the
higher order
higher order
susceptibilities.
susceptibilities.
Higher order susceptibility.
Higher order susceptibilities.
So, but in the
So but
linear,
in the linear,
this is the linear
this is the
optics
linear
approximation.
optics approximation.
Okay.
Okay.
So now,
So now
in
we
case of
in case of
nonlinear
non-linear
optical
optical
processes,
processes,
there are different
there are
frequency
different
generation.
frequency generation.
That is TFG
That is
omega 3
TFG
is equals
omega
to
3 is
omega
equals
1
to omega 1
omega 2,
minus omega 2,
and the other one
and
is
the other one
parametric
is
down
parametric
conversion.
down conversion.
And
And
we can
we can
do the
we can do the
parametric
parametric
amplification, that is
amplification,
pump
that is
photon
pump photon
plus signal
plus
photon
signal
will
photon
give us the
will give us
amplified
the
signal
amplified signal
plus the
plus
idler
the
photon.
idler photon.
So how can we
So how
represent
can
it
we represent it
on the
on the
suppose this is
suppose this is
ET
ET
electric field,
electric field,
this is time.
this is time.
So
So
for the
for
pump
the
signal is
pump signal
constant.
is constant.
Then if there is a
Then if there
vacuum
is a
state,
vacuum state,
vacuum state is
vacuum
constant
state is
in time.
constant in time.
Whereas
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 for the
for the
so this
so
is the
this is the
squeezed amplitude
squeeze
because there
jump
is
because there is
decrement in
decrement
amplitude.
in amplitude.
So this is
So this is
squeezed
squeezed
amplitude
amplitude
fluctuation.
fluctuations.
Okay.
Okay.
So
So
what we saw
what
that
we saw that
if input
if
signal is
input
vacuum
signal is
signal,
vacuum signal,
pump will draw
pump will
energy
draw
from
energy
vacuum
from vacuum
fluctuations.
fluctuations.
If in
If
because if
input
there's a
because if
constant
there's a
time,
constant time,
it
right?
was like this
It was
vacuum
like this
state.
vacuum state.
So now
So now
what will pump do?
what will
Pump
pump
will
do?
draw
Pump
energy
will
from
draw
vacuum
energy from
fluctuation,
vacuum
then this
fluctuation,
is
then this
converted
is
into
converted into
squeezed vacuum.
squeezed
That is
vacuum.
reduced
That is
amplitude.
reduced amplitude
The
noise.
amplitude
The
squeezed vacuum
amplitude
is
squeeze vacuum
fluctuation
is
field
fluctuation
amplitude
field
reduced
amplitude
below
reduced
short
below
noise.
short
So
noise.
what is the
So
takeaway?
what is the
That
takeaway?
squeeze
That
states push
squeeze
the
states
quantum
push the
limits
quantum limits
of measurement
of
precision
measurement precision
and enabled
and enabled
gravitational wave
gravitational
detection,
wave
quantum
detection, quantum
communication, and
communication, and
metrology,
metrology,
and demonstrate
and
that why
demonstrate that
fundamental
why
research is
fundamental
essential,
research is
practical
essential,
benefits
practical
often.
benefits often.
So now
So now
we will take the
we
10
will take
minutes
the
break,
10
then we
minutes
will
break, then
restart.
we will restart.
Okay, so let's
Okay, so let's
restart. Let's
restart.
resume
Let's
that.
resume that.
So
So
now
now
we have
we
discussed the
have
photon
discussed the photon
statistics,
statistics,
photon
histogram for
number
photon number
distribution.
distribution.
We introduced
We
the
introduced the
second order
second
correlation
order
function,
correlation
that is
function, that is if G2
at time
at
tau equals to
time tau
0 is
equals
greater
to
than
0 is
1,
greater
then we
than
will
1, that
say
we
the
will say
chaotic
the
or
chaotic
classical
or
light.
classical
If
light.
G2
If G2
at tau equals to 0
at tau
equals to
equals to 0
1, that
equals to
will give us
1,
the
that will give us
coherent
the
light.
coherent
And
light.
if
And if
G2 at tau equals
G2
to
at
0
tau
is
equals to
less than
0 is
1,
lesser than
then it
1,
will be
then it will be
non-classical or
non-classical or
Subpoisonian light. That
subpoisonian
is
light.
quantum
That is quantum
signature.
signature.
Then studied
Then studied
quadratures that will
quadratures that
describe
will
the behavior
describe
of
the
quantum
behavior of
states,
quantum states,
that is
that is
vacuum state,
vacuum
coherent,
state,
and squeeze
coherent, and
states.
squeeze states.
So
So
now we
now
will
we will
need some
need
theoretical
some theoretical
foundation, that is how
foundation, that
light
is
is
how light is described
quantum mechanics.
quantum mechanically.
So
So
we will see
we will
the
see the
foundation of quantum
foundation of
theory of
quantum
light,
theory of light,
and there will
and
be some
there will be some
new terms and
new terms and
concepts.
concepts.
So
So
now we
to
will talk
now we
about
will
the
talk about the
canonically
canonically
conjugate variables.
conjugate variables.
So
So
so we
so we
in
in
classical
classical
Hamiltonian we have the
Hamiltonian we
h is
have the
equals to
h is
p
equals
square
to
by
p
2m
square by 2m
plus half m
plus
omega
half m
square x
omega
square.
square x square.
Why this form?
Why
Because
this form?
in this
Because
case
in this
x and
case
p are
x and p are
conjugate variables.
conjugate variable.
So why do we
So
need a
why do we need a
So
Hamiltonian?
in the
So
classical
in the
physics,
classical physics,
there are we have the
we have the
that
Newton's law
forms
that forms
motion from forces
motion
or
from forces or
acceleration.
acceleration.
But for the many
But for the
particle
many
system,
particle
it
system,
becomes
it
complex
becomes
system. It
complex system and
becomes
Newton's law
cumbersome.
becomes cumbersome.
So what are the
So what are the
alternatives?
alternative? There are alternative like
Hamiltonian
Lagrangian and
formulation.
Hamiltonian formulation.
In that
In
case,
that
we
case, we
don't deal with
don't
force,
deal
we
with
deal with
force, we deal
energy
with
based approach.
energy based approach.
So
So
Hamiltonian
Hamiltonian
equals to
equals to is a
sum of the
sum
kinetic
of the
energy plus
kinetic energy
potential
plus
energy
potential energy
that is expressed
that
in
is
terms of
expressed in terms
conjugate
of
variables.
conjugate variables.
So now,
So now,
what are the
what are the
Hamiltonian equations
Hamiltonian's
of
equations of
motion?
motion?
So
So
dp by dt
dp by
equals
dt is equals to
minus,
minus
so curl,
so curl
this is curl
this is
p by
curl
curl
p
t
by curl t is equals to
minus
minus
dou h by
dou
dou
h
x,
by dou x.
dou x
Similarly,
by
dou
dou
x
t
by dou t
is equals to
is
curl h
equals
by
to curl h by curl p.
okay.
Okay.
Now
So now,
if h is
if
equal to
h is equals to
by
p
12
square by
plus half
2m plus
omega
half m
square x
omega
square
square x
dp
square
by dt
dp by dt is equals to
minus
minus
omega
m
square
omega
x that
square
will
x.
give you
That
us
will
the
give you us
Hooke's
the
law.
Hooke's law.
Similarly,
Similarly,
if there is
if
the
there
x
is
by
the
dt
x
that is
by
p
dt
by
that is
m
p
that will
by
give
m
us the
that will give us
velocity.
the velocity. So
X and p
x
both
and p both
are the
are the
canonically.
canonically conjugate variable.
What if we
What
have
if we
v
have v
that is
that
velocity
is velocity instead
p
of p,
that is h
that is
equals
h
to
is
half
equals to
mv
half
square
mv
plus half
square
m
plus
omega.
half m omega.
So
So
curl p by
curl p by curl t is equals to minus,
and the
and
other is
the other is
by
dou x
t
by dou t is
to this.
equals to this.
So when we will
So
talk
when we will
about
talk about
force, f is
force,
equals
F
to
is
minus
equals to minus m omega square x,
that is minus
that is minus
Hooke's
kx Hooke's law.
and if we will
And if
the
we will do
x
the
by d
dx by dt,
that will give
that
you
will give
p by
you
m.
p by m.
Okay,
Okay.
velocity.
Velocity and acceleration.
Now,
Now,
if in case
if
of
in case of
this,
this,
if we will do
if we will do curl
x by
dou x
t,
by dou t,
just replace
just replace p by v.
a is not
A is
equals to
not equals to
minus m
minus m omega square x,
and v is
and v is not
and
equals
v.
to mv.
So that is
So that is
v and x
v and
are not
x are
conjugate
not conjugate
pairs and
pairs, and
v and x
v and x,
it means
it means
v and
v
x
and x
don't
don't
satisfy the
satisfy the
Hamiltonian equation.
Hamiltonian's equation.
So what is the
So what is the importance of
canonically
canonically
pair that is the
conjugate pair? That is they obey Hamiltonian
we
equation
just saw
motion.
that
We
if
just
we
saw that
replace
if
it
we
by
replace it by
v, then it
v,
doesn't
then it
follow
doesn't follow
Hamilton's
the
equation to
Hamilton's
motion.
equation to
That is, we are not
motion. That
getting
is, we are not getting the
momentum and the
momentum
force.
and the force.
And
And
other conjugate
other
pairs are
conjugate pairs are
field and
electric
time,
field and
angular
time, angular moment, angle and
momentum,
angular momentum.
and these
And
conjugate
these
pairs are
conjugate
linked by
pairs
the
are linked by the
uncertainty relation,
uncertainty relation,
which allow the
which allow the
straightforward transition
straightforward
to the
transition
quantum
to the
formulation.
quantum formulation.
So now
So
Hamiltonian
now
of a
Hamiltonian
harmonic
of a
oscillator.
harmonic oscillator.
So how can we
So
go
how can
from
we go
classical to
from
quantum
classical to
Hamiltonian?
quantum
So
Hamiltonian?
we can
So
replace
we
the
can
classical
replace the classical
variables
variables
by operators.
by
That is
operators.
x
That
is
is x
x
is x
cap,
cap,
x is x
x is
cap,
x cap,
p,
p,
p cap.
p
Okay.
cap. Okay.
So define
So
x is
define
equals to
x is
x
equals to
and p
x
is
and
equals to
p is
minus
equals to
iota
minus
h cross
iota
t
h
by
cross t
dx.
by dx.
So
So
Now
now
we will prove
we will
that
prove that
the value of
the value of
P in the
P in the
quantum.
quantum.
So if we
So
want to
if
find
we
out the
want to find out the
expectation value,
expectation value A,
it is given
it is
by
given by
integral over
integral over volume
psi star
psi star R A
psi r.
psi R.
Okay.
Okay.
So similarly,
So similarly, we can find
the expectation
the
value
expectation value of P
in the region.
in the region.
Suppose we have
Suppose we have the one box,
or just
or just
then the value
then the value of X
minus L.
minus L by 2 to L by 2. So
If the length will
if the
change,
length
then
will
the
change, then the
constant will also
constant
change.
will also change.
E iota
E iota
kx x
kx
e
x
minus
e
iota
minus iota
kx
kx
and dx.
and
This
dx.
is
So
this
in
is
this
the
region, this is an odd function. It will give you 0.
the value of x.
The value of x is 0.
Now
Now
the value of
the value of
p.
P.
So
So
similarly,
similarly,
minus iota
minus iota h cross
k
iota k
1 by L
1 by L
minus L by
minus L by 2 L by 2
dx
dx, and it
h
will give you
cross.
h cross k.
So now
So now
we got the
we got the
x is equal
x
to
is equals
0,
to 0,
whereas the
whereas the
expectation value
expectation value of
is h
P is
cross
h
k.
cross k.
So the
So
operator
the operator
forms
work only when
work
variables are canonically connected.
this let us
Let
describe
us
light
describe
as a quantum
light as a quantum harmonic
oscillator,
oscillator,
and
and
we will
we will
the quantization
show the quantization of the
of
electromagnetic
quantum.
field for the quantum picture.
So in quantum
So in
mechanics,
quantum
we deal with the
mechanics, we deal with the
probabilities,
probabilities,
exact
not
values,
exact
so that
values,
we
so that
the
we
wave
use the
function to
wave
represent
function
the
to
states,
represent the states.
and this is the
And this is
expectation value
expectation value of
A, just
A,
like we
just
defined
like we
this
define
will 0,
this will
this will h
0, this
cross
will h
k,
cross k.
and then
And then
we took the
we
example
took
of
the
psi equal
example of psi
to
x for
wave,
the plane wave, and
the reason
and
minus
the
L
reason
by 2,
minus L by 2 to L by 2,
we
and
compute the
we'll compute the
expectation values.
expectation
So
values.
now we
So
want
now we want to
evaluate the
evaluate the
commutation relation,
commutation relation,
that is
that is
so
xp. So
xp we want to
xp, we want to find out
xp.
xp.
So
So
xp psi,
xp psi,
which is
which
x,
is
and p
x, and
equals to
p equals to
minus
minus iota
h cross
h cross
psi,
psi,
which will give
which
us
will give us
minus
minus
h
iota
cross
h cross
dou psi by dou.
dou psi by dou x.
Similarly,
Similarly,
px psi
px
is
psi
equals
is
to
equals to
minus
minus iota
dou by dou.
dou by dou x x psi.
So minus,
So minus iota h cross.
so we'll
So
apply the
we'll
product
apply the product rule here.
x
X
del psi by
del psi by del x minus iota h cross psi.
so if we
So if we
x to
x
xp
to xp
minus
minus
px,
px,
it will give us
it will give us the iota
psi.
h cross psi.
It means
It means
X and P
X and
doesn't
P doesn't
commute.
commute.
If
If
XY is
X
equal
Y
to
is equals to
YX,
YX,
what does it
what does
imply?
it
X
imply?
and Y
X and
commute,
Y
and we can
commute, and we
determine
can
the value
determine
of
the
X
value
and
of X and
Y at the same
Y at the
time
same time
simultaneously.
simultaneously.
But X and
But
P
X and
are
P
not
are
commuting
not commuting
with each other.
with each other.
It means
It means
uncertainty relation
uncertainty
exists.
relation exists.
Means we cannot
Means we
define the
cannot
two
define the two
variables
variables
simultaneously with
simultaneously
precision.
with precision.
So now we
So
found
now
out
we
that
found out that
the value of
the value of
XP,
XP,
this is
this is
commutator
commutator
XP
XP
will give us
will give us
iota H
iota
cross,
H cross,
and the
and the
uncertainty relation
uncertainty
will
relation will
exist.
exist.
So meaning of the
So meaning of the
commutator, if A
commutator, if
equals to
AB
0,
equals to
operator
0,
commute, we
operator
can measure
commute, we can measure
simultaneously. If AB is
simultaneously.
not
If
equals
AB
to
is
0,
not equals to
operators
0,
are
operators are
conjugate.
conjugate,
There exists
and
an
there exists an
uncertainty relation
uncertainty
between these
relation
two
between these two
variables.
variables.
Next is
Next is
Hamiltonian. So we
Hamiltonian.
introduce
So we
operators in
introduce
quantum
operators in
mechanics,
quantum
and
mechanics,
what the
and what
Hamiltonian
the
for a
Hamiltonian
quantum
for a
harmonic
quantum
oscillator,
harmonic oscillator,
p square by 2m
p
plus
square
half
by
m
2m
omega
plus half
square x
m
square.
omega square x
Now
square.
our goal is to
Now our
find
goal is to find
eigen
eigen
values and
values and
eigenfunctions
eigenfunctions
of
of
the harmonic
the
oscillator.
harmonic oscillator.
So we will
So we will
initially we solve
initially we
this
solve the
Schrodinger equation
Schrodinger
directly
equation directly
by using the
by using
parabolic
the
potential.
parabolic potential.
Now,
Now,
what was the Dirac
what was the
idea?
Dirac
So
idea?
we defined
So
the
we
two new
defined the two new
parameters,
parameters,
new
new
operators, that is
operators,
A,
that is A,
annihilation,
annihilation,
or lowering,
or lowering, or
creation, Edegger,
creation, Edegger,
or raising
or
operators.
raising operators.
So
So
we have
we have
H
H
is equals
is
to
equals to
P square
P square
by 2
by 2m
half m
half
omega
m
square
omega
x.
square x square. Okay,
We can write
we
it
can
as
write it as
1 by 2
1 by 2m
px square
px
plus
square plus
m
m
square
square omega square
square.
x square.
Okay.
Okay,
So now
so
we can
now we
define
can
A
define
is equals to
A is equals to
1 by root
1 by root
mh
2
cross
mh
omega
cross
m omega
omega
x
m
plus
omega
iota
x
p,
plus
which is
iota p,
x
which
plus
is
iota
x
y,
plus iota y,
x minus iota y
x
is
minus
equals
iota
to
y
x
is
square plus
equals to
y
x square
square.
plus y square.
So similarly,
So
A dagger
similarly,
1
A dagger 1 by
by mh
root 2
omega m
mh
omega x
omega m
minus
omega x
iota.
minus iota p.
So x plus
So x
iota
plus iota
by x
by
minus
x
iota.
minus iota by.
And if we will
And if we
product
will
it, that will
product
give us
it,
x
that will
square
give
plus
us
y
x
square,
square
then
plus
we
y
will get
square. Then
the
we will get the
Hamiltonian. So
Hamiltonian.
now we
So
want to
now we
calculate
want to
the
calculate the
A dagger
A dagger
product. So
product. So A
A dagger is
A
equals
dagger
to
is equals to
1 by
1 by
2m
2m
h cross
h
omega
cross omega
m omega
m
x
omega
plus
x plus
iota
iota
px
px
m omega
m
x
omega
square
x square
minus iota
minus iota
px.
px.
Okay.
Okay,
Next
next
step 1
step
by
1 by
2
2
cross
ms
omega
cross omega
m square
m
omega
square
square
omega
x
square
square
x cap square
plus px
plus
square
px square
minus
minus
iota m
iota m
x
omega
cap
x cap
px square
px cap
plus iota
plus iota m omega
px
px
x square.
x cap.
So now
So now
m square
m
omega
square omega square
x square
x square
plus px
plus
square
px square
minus
minus iota m omega
x cap
x
p
cap p cap
minus
minus
ex cap.
ex cap x cap.
This
This we know the commutation relation that will give us the iota h cross.
it's similar.
It's similar.
Iota
Iota m omega
h,
iota h,
and it will
and
give us
it will give us the
1 by 2
1 by 2 m
h
h
omega.
cross omega.
So we will
So we will
take inside
take inside it
px square by
px
2
square by 2m
plus 1
plus 1 by 2 m omega square
x square
x square
plus h
plus
cross
h cross omega
by 2.
by 2.
Similarly,
Similarly,
so this is the value of
this is the
a.
value of a degree.
Similarly, we
Similarly, we can
find out the value
find out the value of
a digger.
a dagger a.
So when we will
So
do the
when we will do the a dagger a,
we will get the
we will
1
get the 1 upon h
omega
cross omega
px square
px
by
square by
2m
2m
plus 1
plus
by 2
1 by 2
m omega
m omega square
x square
x square
minus half
minus
h
half
cross
h
omega.
cross omega.
This is the
This is the
equation.
equation 2
First for
and
the
the first
a
for the a dagger.
so I'm writing
So I'm writing
this is
in, okay,
considered as
consider
equation
it as
1.
equation 1.
A digger
A
1 by
dagger
h
1 by
cross
h
omega.
cross omega
So now
So now, if we
see the
see the
commutation relation.
commutation relation,
A digger
A dagger
is equals
is
to
equals
A
to A
A digger
dagger
minus A
minus
digger.
A dagger A.
That will give us
That
the
will
1
give us the 1 upon h
omega
cross omega
is equals to
is
1
equals
by
to 1
h
by 2
cross
h
omega
cross
plus
omega
1 by
plus
2
1
h
by
cross
2
omega,
h cross omega,
which will give us
which will
the
give us the
h cross
h
omega.
cross omega, and
Now
we
that
found out that
A digger is
A dagger is
1,
equals to 1,
and that is
and that is
equivalent to
equivalent to
also
also
A
A
digger
A
is equals
dagger
to
is
1
equals to 1 plus
A digger A.
A dagger A.
So these two
So
are
these two are important relation.
the commutation.
The commutation
A
means
and A
A
digger
and
are
A
also
dagger are also,
these also
these
doesn't
also
come.
doesn't come here.
So now
So
if we
now,
want to
if we
write
want to
our
write our Hamiltonian
terms of
in terms of
annihilation and
annihilation and
creation operator,
creation
we can
operator,
write
we can write
from
from
equation 1,
equation 1,
that is
that is H is equals to
H cross
H cross omega
A dagger A
A dagger A
plus half H
plus half H
omega,
cross omega,
that is H
that is
cross
H
omega
cross omega
A dagger
A
A
dagger
plus
A
1.
plus 1 by 2.
And
And
this is from
this is from
equation 1
equation 1.
when A
When
dagger A.
A dagger A.
And from the
And from the
A dagger, that
A
is from
dagger, that is
equation
from
2,
equation 2,
we get
we get
H is
H
equals
is
to
equals to
H cross
H
omega
cross omega
A dagger
A dagger minus
minus 1.
minus 1 by 2. So
that's what the
that's
conclusion
what the
part.
conclusion
Find
part.
out
We
that
find out that the A
like
dagger can
this,
be
A
like
dagger
this. A dagger
is
A
equals to 1
is
upon
equals to
h
1
cross
upon h
omega.
cross omega.
And A
Then
dagger
A dagger is
can be written like
can be
this.
written like this. A dagger is equals to 1.
So now we
So
can find
now we
out
can
the
find out the
HA.
HA.
So if you want to
So if you
calculate
want to calculate
commutation relation of
commutation relation of
H and
H and
annihilation operator,
annihilation operator,
so we can
so
write
we
it.
can write it.
What was
What was
H in
H
terms of
in terms of
A?
A?
A dagger, we
A
can
dagger,
write
we can
A
write
dagger
A dagger
minus 1 by
minus
2
1 by 2
H cross
H
omega
cross
into
omega
A
into
dagger,
A dagger,
which
which
H cross omega is
H cross omega
we
is
can
constant,
take
we
it
can take
outside.
it outside.
A
A dagger,
A dagger
A dagger,
A
A
minus
minus
A by
A by 2
minus
minus
A dagger
A dagger
plus A
plus
by
A by 2.
so we will get
So we will get
cross
H cross omega.
A will come
A will come
outside
outside.
dagger
A dagger.
A
A
minus
minus A dagger.
and that will give
And
us
that
the
will give us the
minus because
minus
we
because
know that
we know that
A
A dagger
it's
commutation is 1.
reverse
So it's
A dagger
reverse.
A
A dagger A,
is
it
minus
will
1.
be minus 1.
It will
So
simply
it will
give
simply
minus
give
H cross
minus H
omega.
cross omega A.
So this is this.
So this is this.
Similarly,
So
when we
similarly, when we will do it with the
H A dagger,
H
it
A dagger,
will
it
give
will
the
give us
positive
the
H
positive
omega
H
A.
omega A dagger.
So with the
So with the
annihilation operator,
annihilation
there is
operator, there
minus
is
sign.
minus
With the
sign.
creation
With the
operator,
creation operator,
there is the
there is the
plus sign.
plus sign.
So now
So now
we saw that
we saw that
what
what,
is the
what
effect
is
of
the effect
raising,
of raising,
lowering, and
lowering and raising
operators.
operators.
So we saw
So
that
we saw that
we want to find
we
out
want
the
to
I.
find out the eigen.
So
So
what is the
what is the
eigenvalue equation?
eigenvalue equation?
Okay.
Okay.
So now
So
what
now
is
what is
H
H
A
A
psi n?
psi n?
Okay.
Okay.
So now
So
H
now
A
H
psi
A
n we
psi
can
n,
write
we
it
can
as
write it as
we can add
we
and
can add and
subtract.
subtract.
So
So
H A psi
H A
n
psi n,
A H
A
psi
H
n
psi n
plus just
plus
add and
just
subtract
add and
A
subtract
psi n
A
A H
psi
psi
n,
n.
A H psi n.
Then it will give
Then
you
it will give you
H A
H A
minus A H
minus
psi
A H psi n
plus
plus
S I n is
H
equals
psi n
to
is
E
equals
n
to
psi,
E n psi
right?
n, right?
And then H A
And then
minus
H A
A H, we
minus
know that
AH,
it's
we
a
know that
common.
it's a
We
common.
saw that it
We
will
saw
give
that it will
minus
give a
sign
minus sign
minus H
minus
cross
H
omega
cross
A
omega
psi
A psi n
plus
plus
N
E
A
n
psi n,
A psi n.
and it is
And
E
it
n
is E n
minus H cross
minus H cross omega
A psi n.
A psi n.
What did
What
it
it
give us?
did give us?
We found that
We found that
H A psi
H
n
A psi n
is giving
is
us E
giving us
n
E
minus
n
H
minus
cross
H
omega
cross omega
A psi n.
A psi n.
It what is the
What
conclusion
is the
from that?
conclusion
That is
from that?
A
That
psi
is
n is
A
also
psi
an
n is also an
eigenfunction of
eigenfunction
our
of our Hamiltonian,
where the
where the
eigenvalues is
eigenvalues is
minus
En
cross
minus
omega.
h cross
So
omega.
we found
So
out
we
that the
found out that the
annihilation operators
annihilation
lowers the
operators
energy
lowers
by
the
one
energy by
quantum,
one
that is
quantum, that
by
is
h cross
by h
omega,
cross omega,
which is the
which
lowering
is the
operator.
lowering operator.
Similarly,
Similarly,
similarly we can
similarly
find
we
out
can
the
find out the
h a
h a
dagger psi n,
dagger
which
psi
will
n,
give us
which
the
will give us the
En
En
plus h cross
plus h
omega,
cross omega
a dagger
a
psi.
dagger psi n.
Okay.
Okay.
So now
So
we
now
saw that
we saw
when
that
the
when the
operator A psi
operator
will
A
operate,
psi will operate,
the new state will be
the new
psi n
state will be
minus
psi n
one, and the
minus 1
energy
and
will
the
be
energy
reduced
will
by
be
h
reduced
cross
by h cross omega,
because it
because
lowers the
it
energy by
lowers the
h cross
energy by
omega,
h cross
whereas A
omega,
takes
whereas
psi
A
n,
takes
it
psi n,
increases the
it
energy
increases
by
the
plus
energy
h
by
cross
plus h
omega,
cross
and
omega, and
the new state will be
the new
psi
state will
n,
be psi n
where
plus 1, where
so energy
so
levels are
energy
equal
levels are
space.
equally
Suppose
spaced. Suppose
this is
this
En,
is En,
which is h
which
psi
is h
n,
psi n,
then
then
En
En
minus h cross
minus h
omega.
cross omega.
This is when
This is
one
when
time
one time
A operator is
A
used.
operator is used.
The
If
En
the
minus
En
2h
minus
cross
2h
omega,
cross omega,
the another,
the
so
another, so
2 times.
if two times,
So this gap
so
is
this
h
gap
cross
is h
omega.
cross omega.
Similarly,
Similarly,
A dagger
A
plus
dagger
psi
plus psi n,
En plus h
En
cross
plus h
omega,
cross omega,
En
En
plus
plus
h
2h
cross omega.
cross
This is
omega, and
also
this is also the
h cross omega.
h cross omega.
Now we want to
Now we
find
want to
out
find out the
the ground state
ground state
energy and the wave
energy and the
function
wave
of
function
the harmonic
of the
oscillator.
harmonic
So
oscillator. So
if we are
if
operating
we are operating
A operator
A
on psi
operator
0, it
on
will
psi
give us
0,
the
it will
0
give us
because
the
there
0,
is no,
because there is no,
because
because
if we are
if
already in
we
the
are already
state,
in the
there
ground
is
state, there is,
we can't go
we
below
can't
that.
go below that.
A psi
Okay, so
naught
A
will
psi naught will
give us
be
the 0.
give us the
What
0.
is the value?
What is the value? So this is the
This psi naught,
this psi naught,
this psi naught
this psi naught is the
is ground state.
ground state wave function.
Okay. So
Okay,
what is the
so
value of
what is
A?
the value of
A
A?
is to
A
1
is equals
by
to
root 2
1 by
m
root
cross
2
omega.
mh cross omega,
M omega x
m omega
cap
x cap
at a
at a p
is
cap
equals to
is
0.
equals to 0.
So A psi naught
So
is
A
equal
psi naught
to
is equals to 0, that is
x
m
plus
omega
iota
x
p
plus
psi naught
iota
is
p
equals
psi
to
naught
0.
is
Let's
equals to 0.
suppose
Let's suppose
we are
we are
giving a guess
giving a
that is
guess, that is
psi naught is
psi naught
equals
is
to
equals to
C
c
exponential
exponential
minus
minus
omega
m
x
omega
square
x
by
square by
2h cross.
2h cross.
C is the
C is the
normalization constant.
normalization
Now
constant.
we will
Now we
calculate
will calculate the
minus infinity
minus infinity to infinity, the
probability.
probability.
This is for
This is for
to calculate
to
this value
calculate
of
the
C.
value of C.
So now,
So now,
what is the value
what
of
is the
this d
value
by
of this
dt?
d by dx? Because
In quantum
p in
mechanics, P
quantum
is equals
mechanics,
to
p is
minus
equals
I
to
times
minus
d
i
by dt.
attached to d
So we
by
will
d.
find
So we will find a
cos psi naught by
cos psi
curl
naught
x
by curl x is
minus
equals to
m omega
minus m
x
omega x
by h cross
by
psi
h
naught.
cross psi naught.
And we know
And
that
we know
h psi
that
naught
h
is
psi
equals
naught
to
is equals to,
and then
and then,
so let's
so
assume
let's assume u
just
is
solve this
just solve
integral.
this integral.
U is equals
U
to
is equals
minus
to
m
minus
omega
m
x
omega x square
x
by 2h
cut
cut
x
x and
m omega
m
by h
omega by
cut.
h cut.
Then du
Then
will
du will be
dx.
dx.
So then,
So then,
so
okay.
this
So
we
this
got
we
this we
got,
got.
this we got,
When we will do
and when we
this,
will do
get
this,
this
we will
value
get
of
this
c is
value of
equals to
c is
m omega
equals
by
to
pi
m
h
omega by pi h cross 1 by 2,
and
and
Then we will get the
Then we
value
will get the value of the
state
ground
function.
state wave
Sin of x
function.
is
Sin
equal
of
to
x is equals to m
pi
omega by pi h cross 1 by 4
exponential minus
exponential minus m
by.
omega x square by 2h square.
Now what is the
Now,
ground
what is
state?
the ground state energy?
We will
So, when
apply
we will apply the Hamiltonian on psi naught, we
h
were getting h cross omega
degree plus
a
1
degree
by.
a plus 1 by 2. So,
Since a psi naught
since
is
a
equal
psi naught
to
is equals
x
to
psi
0,
naught
s psi naught
is equals
is
to
equals
half
to
h
half h
cross omega
cross
psi.
omega psi naught.
So E naught is
So, E
equals
naught
to
is
half
equals
h
to
cross
half
omega.
h cross
It
omega.
means,
It means,
what does it mean?
what
It
does it
means
mean?
psi
It
naught
means psi naught
satisfy the
satisfy
Schrodinger.
the Schrodinger equation.
We can
We
calculate
can
it by
calculate it by finding out the.
okay. So simply we
Okay,
can
so simply we
calculate it
can
and
calculate it
substitute
and
the
substitute
values
the values
in the
in the
Hamiltonian.
Hamiltonian.
That is
That
S
is
psi naught
S
is
psi
equals
naught
to
is equals
minus
to minus h cross
by 2m.
by
Our
2m.
Schrodinger
Our
equation
Schrodinger
called psi
equation
by
called
called
2
x
psi by
squared
curl x
plus
square
half
plus
m
half
omega
m omega
square
square x
psi naught.
psi naught.
And we'll
When
substitute
we
it, we will
substitute
get
it, we will get the
half h
half
cross
h
omega
cross
psi.
omega psi naught.
So
So
approach
approach
Schrodinger equation,
Schrodinger
directly
equation will
solve the
directly solve the
differential equation,
differential
get the
equation,
TDS and
effect
explicit
TDS and
form of wave
explicit form
function.
of wave function.
Whereas in
Whereas
operator
in
method we
operator
use
method, we will use
commutation
the
relation,
commutation relation,
easy to solve and
easy to
quick
solve
access to
and
the
quick
eigen.
access to the eigenvalue.
So we had to
So we
prove
had to
that
prove
that psi naught is equals
psi
to m
naught is
omega
equals
by
to m
h
omega by
pi h cross
pi
1 by
h cross
4
1 by 4
exponential minus m
exponential
omega
minus m omega
by
x
2h
square
cross
by
satisfy
2h
the
cross
Schrodinger.
satisfy the Schrodinger
So
equation. So
that
we solve that
sin is equals to
sin
p
is
n
equals
psi
to
n.
en psi n.
So
So
our sin naught will
our sin
satisfy
naught will
that.
satisfy the.
Now coming to the
Now coming to
assignment.
the assignment.
So phasor
So phasor
diagrams
diagrams
corresponding to x1
corresponding to
minus
x1 minus x2.
quadrature fields are
Quadrature
shown in
fields are
figure
shown
1.
in figure
So
1.
we have
So we
here
have
given the
here
six
given the
figures.
six figures.
So what is the
So
first
what is the
question it's
first
asking? So
question
we
is
saw that
asking? So
this
we
is
saw that this
A.
is A.
In this case, it
In this
was for
case,
the
it was for
coherent
the
state,
coherent state,
where it was
where it was
representing the alpha.
representing the alpha.
This is for the
This is
phase
for the
field.
phase
This is
field.
for
This
the
is for
photon
the photon
number states.
number
This is
state.
for
This
the
is for
squeezed
the
vacuum
squeezed
states.
vacuum states.
This is for the
This is
vacuum
for the
state.
vacuum state.
Because
And
it's at
these,
the
because it's
center,
at the center,
so there is
so there is
no photon. That's why it's vacuum.
vacuum,
And
and
it is the
it is
amplitude
the
squeeze.
amplitude
Now the
squeeze.
first
Now
question
the
is,
first question is,
choose the correct
choose
phasor
the
diagram
correct
that
phasor
represents
diagram
the
that
coherent
represents the
state.
coherent
So
state.
the
So the
coherent state.
coherent state.
So that
We
for
saw
the
that for
coherent
the
state,
coherent state,
it will be like this
it will be
because
like this
delta
because delta n is equals to
root n bar and
root
here
n bar, and here it
represented
is
by alpha.
represented
This
by alpha. This
length will be the
length
same
will be
as
the same as
n bar.
n bar.
So here
So here
delta x1
delta
is equal
x1
to
is
delta
equals to
x2
delta x2 is
half.
equals to half.
So the option
So
A
the
is
option
correct.
A is correct.
The next question
The
is
next
correct
question is
phasor
correct
diagram that
phasor
represents
diagram that
vacuum
represents the
field.
vacuum field.
For the
So
vacuum
for the
field, we
vacuum
will give
field, we are given the
if it is at the
if it is
center.
at the center.
So this is
So this is
vacuum field or
vacuum field or
coherent vacuum.
coherent vacuum state.
Okay.
Okay.
So the option
So
is
the
E.
option is E.
The next is
The
choose the
next
correct
is choose
phasor
the
diagram
correct
that
phasor
represents
diagram that
photon
represents the
number state.
photon number states.
We saw that the
So we saw
circle
that the circle
represents the photon
represents the
number
photon
states,
number states,
whereas the radius
whereas the
represents the
radius
number of
represents the
photons.
number of photons.
So the option
So the
C.
option C.
Now choose the
Now
correct
choose the
phasor
correct
diagram that
phasor
represents
diagram that
squeeze
represents the
state.
squeeze states.
So see
So
in this
see
figure,
in this figure,
this is the
this
squeeze
is
state,
the
this
squeeze
is the
state,
squeeze state, and
this
this
is
is
the
also
squeeze
this is the
state, and
vacuum.
this is also, so this is the vacuum.
This is the vacuum squeeze
This is the
state, and
vacuum
these
squeeze
two are
state,
the
and
phase
these
and
two are the phase and
amplitude squeeze states.
amplitude squeeze states.
So B,
So
D, and F.
B, D, and F.
So the correct option
So
is
the
B,
correct
D.
option is B, D, and
The
F.
next question
The
is
next question is
choose the correct
choose
pairs
the
of
correct pairs
uncertainty
of
relation.
uncertainty relation.
So
So
we saw
we saw
delta
delta
x1, delta
x1,
x2
delta
is greater
x2
than
is
1 by
greater than
4,
1 by 4,
not 1 by 2.
not
So
1 by 2.
this is
So
correct.
this is correct. Then
Delta x,
delta
delta
x,
p
delta
is
p
greater than
is
h
greater
cross
than
by 2
h cross
since
by 2
x
since
and p has
x and
some
p
units.
has
So
some
it is
units.
the
So it is the
here it there will
here
be
it
h
there
cut,
will be h
whereas
cut,
x1 and
whereas
x2
x1
are
and x2 are
dimensionless.
dimensionless.
So that's why
So that's why
in the
in the
uncertainty relation there
uncertainty
was no
relation
h
there was
cross.
no h
So this
cross.
is
So this is
incorrect and this is
incorrect. This is
then
correct. Then
delta n and
delta n
delta
and
phi
delta
is
phi is
greater than 1 by
greater
2.
than 1 by 2.
So these three
So
are
these
correct.
three are correct. These are
So
so
we have
we have
assignment is
assignment is
today's assignment is
today's
very
assignment
easy.
is very easy.
All the
All
questions
the
are we have
questions are we have
already done in the
already done in
lecture,
the lecture,
and we have
and
revised
we have
and
revised
write
and
all these things.
derived all these things.
So the next is
So the
given
next
below
is
are two
given below are
statements
two
in regard to
statements in
measurement
regard to measurement
noise
sensitivity and
levels.
noise levels.
Sensitivity in the
Sensitivity in the
substitute one is
substituent one
sensitivity
is
in the measurement
sensitivity in the measurements
can be improved
can
by
be
reducing
improved by
noise below
reducing
short
noise
noise
below
limit.
short noise limit.
And the statement 2
And the
is
statement 2
subpoisonian
is
light can
subpoisonian
have
light can
noise
have
below
noise below
short noise level.
short noise level.
So we saw
So
that
we saw that
if
if
delta n is
delta n
lesser
is
than n
lesser
bar,
than n bar,
if delta n
if
is equals
delta
to
n is
0,
equals
then
to
we will
0,
have the
then we will
perfect
have the perfect
subpoisonian light.
subpoisonian light.
And
And
if we have
if we
the
have the
squeeze light
squeeze
that
light
reduce
that is
below the
reduced below
short
the
noise,
short noise,
the
we can
fluctuation
the
will be less
fluctuation
and
will
we
be
can
less and
detect
we
it
can
better.
detect it better,
Because
because
in that
in
direction,
that direction,
if the phase is
the phase is
if the number of
if the
photons
number
is
of
below the
photons is
mean,
below the mean,
that is it is below
that is
the
it
short
is below
noise
the
limit,
short noise limit,
we
and
are reducing
we are reducing the
fluctuations,
fluctuations, we are reducing.
that's why we are
That's why
increasing
we are
the
increasing the
sensitivity of the
sensitivity of
measurements
the
by
measurements. We are
reducing the
by
noise.
reducing the noise.
And
And
this this
this
condition
this
represents
condition represents the
subpoisonion.
subpoisonion.
So
So
statement
statement
subpoisonian light can have
subpoisonion light can have noise
below short noise limit.
below.
Statement S1 is
Statement
true
S1 is true
and statement
and
S2 is true.
statement S2 is
Both the
true. So
statements
both
are
the
true.
statements are true.
Next question
Next
is
question
squeeze
is
state is
squeeze
said to be
state is said to
detected
be detected
when the
when the
fluctuations in
fluctuations
differential
in differential
current
in
del I
current del
output
I
are
output are
we just saw.
we just saw.
Squeeze state
Squeeze state
when we can detect
when
the
we can
squeeze
detect
state
the squeeze state
when it is
when
below
it is below
the
output is
short
below
noise.
the short noise limit.
So it should be
So it
below the
should
short.
be below the short noise limit.
Next, choose the
Next,
correct
choose
option
the correct
in
option
regard to
in
operator
regard
A.
to operator
So
A.
A is
So
the
A is the
annihilation operator
annihilation operator
or
or
lowering
lowering
operator.
operator.
So first of all, it
So
is a
first of all, it is a
lowering operator.
lowering
It's not a
operator. It's
raising
not a
operator.
raising
It's
operator. Raising operator is a digger.
now when
Now,
H A
when
acts
H
on
A
psi n,
acts on
it
psi
gives
n,
an
it gives
eigenvalue
an
equal to
eigenvalue
E
equal to
plus H
En
cross
plus
omega.
H
So we
cross
saw
omega.
that
So we saw that
when
when
H was
H
operating
was
on
operating
A,
on A,
HA was operating
HA
on
was
psi
operating
n.
on psi
It was
n,
giving
it
us
was giving
En
us En
because it's an
minus, because it's an
annihilation operator.
annihilation operator.
So the energy
So the
was
energy was
decreasing by H
decreasing
cross
by
omega.
H cross omega.
So it will
So
not.
it will not.
This is
This
correct.
is correct.
So
So
H8 is an
H8
eigenvalue.
is an eigenvalue of
No. So
no,
these two are
no.
correct.
So
It's a
these two are
lowering.
correct. It's a lowering.
It's a low.
It's a low.
It's a lowering
It's a
operator
lowering
plus it
operator
will give
plus
the
it will give
eigenvalue
you
of
the
H.
eigenvalue of En minus H cross omega.
Next is choose the
Next,
correct
choose the
option in
correct
regard to
option in
operator
regard to
A degree.
operator
So
A
A
degree.
degree
So
is
A degree is
creator operator
creator
or
operator or
operator.
raising operator.
So it's a raising
It's a
operator.
raising operator,
We
and
just
we
saw
just saw
H A
H
dagger
A dagger
psi n
psi n.
will
It
give
will
you
give
N
you En
plus H
plus
cross.
H cross omega.
So it is
So it is
increasing the energy
increasing the energy
by
by
H cross by a
H
factor
cross
of
by a
H
factor of
cross
H
omega.
cross omega.
So when H
So
dagger
when H dagger
gives
will, it
eigenvalue
gives an
equals,
eigenvalue equals to
these
H.
two
So
options are
these two
correct.
options are correct.
Next is the
Next is
commutator
the
of two
commutator
quantum
of two
mechanical
quantum
operators
mechanical
A and
operators
B.
A and B is defined as,
This is the
this is the AB is equals to
AB
AB
minus
minus B
A.
A.
Option B.
Option B.
The commutator
The
A
commutator A dagger.
so
So
A dagger will
A
be
dagger will
A
be
dagger
A dagger
minus.
minus.
We in the
We
class
in the
today
class
also we
today
proved
also
that
we proved
A
that
dagger
A dagger,
it will gives you
it will
1.
gives you 1.
The correct answer
The
is
correct answer
A
is
dagger.
1.
The
A dagger,
commutator
the
relation of
commutator
A
relation of
dagger.
A
We
dagger.
know that A is
We know
equals
that
to
A
1
is equals
by
to
root
1
2
by
m
root
cross
2 mh
omega.
cross omega.
We saw
We
right
saw right
in the
in the
class.
class.
That A is equals
That
to 1
A is
by
equals to
2
1 by 2
mh cross omega
mh cross
m
omega
omega
m
x
omega
plus
x plus
iota p.
iota
Similarly,
p.
A
Similarly,
dagger
A dagger
minus
m omega x
factor.
minus iota p.
The next is the
The next is the
commutator H.
commutator H A dagger.
We have
We have
already solved this
already
question.
solved
That's
this
why I'm
question. That's
moving
why I'm
fast
moving fast,
and I took
and
time
I took time
previously.
previously.
That H
That
A dagger
H
is
A
equals
dagger
to
is
H
equals to
cross
H
omega
cross omega
A dagger.
A dagger.
Similarly, H A,
Similarly, H A,
like if there is
like if there
annihilation,
is
there will be
annihilation, there
minus
will be
sign.
minus sign H cross omega and A.
So this is the
So
correct
this is the
answer.
correct answer.
Next is given
Next is
below are two
given below are
statements in
two
regard to
statements in regard
commutation
to
of two
commutation
quantum
of two
operators
quantum
A.
operators AB.
Two operators do
Two
not
operators
commute
do not
if
commute if
AB is not
AB
equals to
is not
0.
equals to
It
0.
will not be
It will
possible to
not be
measure their
possible to
values
measure their values with
arbitrary accuracy
arbitrary
at the same
accuracy
time.
at the same time.
We saw that.
We saw that.
We saw the
We saw
implication
the
of this
implication of
commutator.
this commutator.
If
If
AB is equals
AB
to
is
0,
equals to 0,
operators
operators
commute
commute
and
and
we
we
can
can
calculate values
calculate
of
values of
both
both
variables
variables
operators
operators
simultaneously
simultaneously
with accuracy.
with accuracy.
Okay, but
Okay,
if
but if
AB doesn't
AB
commute,
doesn't
then
commute,
we
then
cannot.
we
It is
cannot.
not
It is
possible to
not
measure the
possible to measure the
values with
values
arbitrary
with arbitrary
accuracy at the same
accuracy at
time.
the same time.
Statement
So
S1 is
statement
true.
S1 is true,
S2 is
S2
also true,
is
and
also
S2
true,
is the
and S2 is the
implication of
implication
S1. So
of
the last
S1. So
option
the
is
last
correct.
option is correct.
The next question
The
is
next
find the
question is find the
commutator of
commutator
eta
of
pi
eta pi
given the
given
operator
the operator
definition.
definition.
Eta is
Eta
equals
is
to
equals to
So we can solve
we
this.
can solve this.
1 by
1 by root 2
a
a
plus
plus a dagger
iota by root
iota by root 2
a dagger
a
minus.
dagger minus a.
So
So
the constant
the
we can
constant we can
outside
keep
iota by
outside
2.
iota by 2.
So first of all,
So
a
first of
will
all, A will
go with a
go
dagger,
with A dagger,
then plus
then plus
a dagger
A
with a
dagger
dagger
with A dagger
minus
minus
a dagger
A dagger
minus
minus
a dagger.
A dagger with A.
So
So
these the
these
computation
the
operator
commutation operators
same
with same
is 0 because
is 0 because
a
A dagger
dagger
minus A dagger is 0.
so this
So
this
this
0.
0 0.
Then
Then
we have
we
iota
have
by 2
iota by 2
a dagger
A dagger minus
a dagger
A dagger A.
we know the
We know
commutation
the commutation relation.
a dagger is
A
equal
dagger is equals to 1.
to hence
Hence,
a dagger
A dagger A
is equals to
is
minus.
equals to minus
So
1.
we will
So
substitute
we
the
will substitute the values of iota by 2,
1
1
minus
minus
minus 1.
minus 1.
So that is iota by
So
2
that is
into,
iota by 2
so we will
into,
get the iota.
so we will get
The
the
correct
iota.
option
So
is
the correct option is
iota.
iota.
The last
The
question is
last question is
which of the following operate
which of the
pairs
following
do not
pairs do not commute?
so position
So
x and
position X and P.
so we saw
So we
that
saw that
the x and
the
p
X and P
is iota
is
h.
iota H cross.
It's not equal to
It's
0.
not equal to 0.
So that's why
So that's why
this
this
x and p
X and
don't
P
convert.
don't commute.
Then h and
Then H
x,
and X.
h and
H and
x, it gives
X,
us
it
0.
gives
So
us
that's why
0.
it's
So
common.
that's why it's commute.
H and a
H
dagger.
and A
So we
dagger.
saw
So we
that
saw that
H and dagger
H and dagger was
plus
giving
H
us
omega.
H omega A dagger.
It means it
It means
also
it
doesn't
also
come.
doesn't commute.
Then
Then
annihilation A
annihilation
and A
A
dagger.
and A dagger.
So we saw
So
that
we
the
saw
value
that the
A
value of A
dagger is
and A dagger is equal
to 1.
to
So
1.
A and
So
A dagger
A and
also
A
will
dagger
be.
also don't commute.
So if the
So if the
commutation is
commutation
equals
is
to
not
0,
equals to 0,
then it
then it
doesn't commute. So
doesn't
the
commute.
X and
So
P
the
doesn't
X and P
commute,
doesn't commute,
H and A dagger
H and
doesn't
A
commute,
dagger
and
doesn't
A and
commute,
A
and
dagger.
A and A dagger doesn't commute.
Okay, so
Okay,
thank
so
you all.
thank you all.
So today
So
we
today we
discussed in detail
discussed in detail
about the squeeze
about the
state,
squeeze state,
photon
photon
states,
number states,
and
and
canonical
canonical
variables, and
variables,
quantum
and the
harmonic
quantum
oscillators,
harmonic
and how
oscillators, and
are we
how are we
moving from
moving
classical to
from
quantum
classical to quantum harmonic
oscillators,
oscillators,
and solve
and solve
all the
all the
commutation
commutation
relations.
relations.
So this was all
So this
about
was
today.
all about today.
In the next
In
class,
the
we will
next class, we will
learn about
learn
the
about the
little bit in
little
detail
bit
about
in
the
detail
quantum
about the
light.
quantum light.
Okay, so thank you.
Okay, so thank you.